Welcome to Chapter 6. This is going to be a lesson covering the calculation and a little bit of the concept from sections 6.1 to 6.3. We're going to talk mostly about thermal energy and heat capacity and how they apply to our calculation problems. It's worth having a quick pause right now, though, and reading this quote. This is from a book I've been reading on physics instruction. Take a read of this paragraph and decide whether something in here maybe applies to you, if there's something here that gives you a hint as to the kinds of things you can maybe do. But just as importantly, once you've read the quote and thought about it, try this exercise for Monday. And I'd like it if you were able to do that right at the beginning of class. As soon as you arrive, find somebody else and pass your question on to them, your conceptual question. So pause, read, and then continue with the lesson. Okay, so we're talking about thermal energy. We've been talking about kinetic energy, gravitational potential energy, work, and that sort of thing. Now what we're going to do is we're going to imagine a single molecule moving around. Because when you think about it, the kinetic molecular theory tells us that everything is made up of particles, and those particles are constantly moving. And you may remember from various parts of your kinetic molecular theory that particles are moving around and they are attracted to each other. So when they're not moving very quickly, it's easy for them to get stuck together. And that, when they're stuck together and unable to move around each other, that's a solid. When they're moving a little bit and they've got some energy, they can get away a little bit so they can slide past each other, that is a liquid. And then when they have enough speed that they're not actually bonded to each other at all, that's a gas. Now, we also know that solid, liquid, gas generally go in the colder to warmer to hotter direction. And thermal energy really explains that, covers that. If you imagine a single molecule, and we go back to our energy unit, the first chunk of the energy unit, anything that's moving and has mass, and any molecule, any particle, any atom has mass, if it's moving, that means it has kinetic energy as well. So when it moves, let's put that back together, when it moves, it has kinetic energy, 1/2 mv squared for any one molecule. The faster it's moving, the more kinetic energy it has. Now if we look at a whole bunch of these, and they're all moving around, I can't get them all moving at the same time, but I'm sure there are animations that'll show you. They're all moving at the same time. If they're all moving, they're moving with different speeds in different directions. Usually they have the same mass if it's one substance, but if there are multiple substances there, they can have different masses. So there are a whole bunch of different kinetic energies going on in that system. So if you've got a container full of gas, there are billions of air molecules in there, and they're all racing around at different speeds, colliding with each other, transferring energy, but they all have kinetic energy. And if we were to add up all those kinetic energies and take the average, divide by the number of molecules, we would get a number that's proportional to the temperature of that substance. So a definition of the word temperature, which you use in everyday life, is the average kinetic energy of the molecules in a system. So we take molecules, we assume they have a certain average kinetic energy, or a certain kinetic energy. The average, if we've got a system, a bucket, a container of some substance, the average kinetic energy of the molecules in that substance multiplied by some constant gives you what we're calling the temperature. Now, we have 3 degrees scales of measuring temperature, and I'll do a little conceptual lesson on temperature on Monday. But the 3 scales we use, and they're all developed in different ways. We have absolute, which is measured in kelvins. We have Celsius, which is measured in degrees Celsius, and we have Fahrenheit, which is the imperial system. Celsius is the metric. And all 3 have their own uses and are used more or less often. Now, a little exercise for you. Pause the video when you've heard this, but read the description at the top. What I would like you to do is I have a scale here of Celsius versus Fahrenheit. What I would like you to do is, looking at these numbers, this is a mathematical exercise, try to work out a relationship, a y equals mx plus b relationship between these two values, these two temperatures. The scale, this is the translation, so negative 40 Celsius is negative 40 Fahrenheit, negative 30 Celsius is negative 22 Fahrenheit, negative 10 Celsius is 14 Fahrenheit, and so on. So try to work out a relationship between the two. The reason we work out a relationship is so we can convert. So pause the video now, see if you can do that. Okay, presumably you have worked out some sort of relationship or tried and maybe failed. And the question I ask to give you a hint is, if a relationship is linear, what do you need? What do you need to define that relationship, that conversion? And it's really what we need to define any scale. Anytime we build a scale, a temperature scale, a measurement, a distance measurement scale, a time scale, we have to have two things. We have to have a reference point, and we have to have a graduation. So in the case of a scale, the Celsius scale, we chose a 0 point, which is the freezing point of water. And we chose a scale so that 100 degrees, from the distance from 100 degrees Celsius, or from 0 to 100 degrees Celsius, that the 100 gradations, or 100 degrees, brings us to 100 degrees Celsius, which is the boiling point of water. So this gives us a reference point, and it tells us that 1 degree Celsius is a certain amount. 100 of them are equal to the temperature difference between freezing and boiling water. So when you're working out a relationship between two values, that gets into linear relationships. And for linear relationships, you need an intercept and you need a slope. The intercept here, the easiest way to think about it is, there's a point where the two values meet. There's a point, a temperature, at which the measurement in degrees Celsius and the measurement in Fahrenheit are equal, negative 40 degrees. And I'll point something else out here, which is, when you increase by 5 degrees Celsius, you increase by 9 degrees Fahrenheit. So that gives you a slope, 9 Fahrenheit for 5 Celsius. So see if you can work out the relationship from there. And once you've tried, once you've given it your best shot, look up the conversion. There are two ways to convert between the two, and I'll show you my way, but the way that you'll find on the internet is easier to write down if you want. Okay? So let's move on to heat capacity. Oh, quick word about Kelvin first. Kelvin is a measure in degrees Celsius, the same thing, so 1 Kelvin is equal to 1 degree Celsius in terms of gradations. But 0 Kelvin is equal to negative 273.15 degrees Celsius. So 0 degrees Celsius is going to be 273.15 Kelvin. You'll notice that when I'm talking about Celsius or Fahrenheit, we actually say the word degrees. When we're talking about Kelvin, we don't say the word degrees. It's just 273 Kelvin. And the reason we have an absolute zero scale is 0 Kelvin is the point where all the molecules in a substance have 0 kinetic energy. So it's the point where there is no thermal energy left, which is why we call it absolute zero. All right, I think we're going to move to heat capacity now. So I'm going to pause. I'm going to stop this video because it's getting long enough. Hopefully that combination is good enough for you for now, and we will start the next video now.